let's look at example 5.5. And in this case, we have a piston cylinder. It has 2 kilograms of helium. It has 300 K, 100 kPa. The heat loss is equal to 100 kilojoules. And we know that P2 is equal to 600 kPa. And the temperature T2 is equal to 450 K. So when I look at our process, we do a sketch. The substance is helium, so it's an ideal gas. So I can use the ideal gas equations of state. The process, we don't know. And is energy involved? Yes. So I know that we can start off and use the first law of thermodynamics. That tells me my next step is to do that. So just as we learned in chapter 3, chapter 4, chapter 5, and continuing. So now I know Q is equal to delta U plus W plus delta KE plus delta PE. There's no change of kinetic or potential energy, and in this case the gas is compressed, so it's being compressed, raising its pressure and temperature. We just don't know the process. We know that Q is equal to minus 100 kilojoules. So you have to pay attention to heat out being negative and use the correct sign convention. Delta U is equal to mc sub v T2 minus T1. So this is 2 times C sub v is 3.1189 times 450 minus 300. So delta U is equal to 935.7 kilojoules. And I can solve for W. So W is equal to Q minus delta U. So it's equal to minus 100 minus 935.7, where the work is equal to minus 1035.7 kilojoules. So of the 1035 kilojoules that were put in, 935.7 increased the internal energy, and 100 was lost, is heat that left. I can find the final volume. You're asked to find V2. It's equal to mR T2 over P2. So it's equal to 2 times 2.077 times 450 over 600, where the V2 is equal to 3.12 cubic meters. So in this case, we use the ideal gas law equation of state to find the final volume. We use the first law, as we're used to, for finding the work. We didn't know what the process was. Now what I'd like to do is look at example 5.6. So that's in the text. And I'll go through this in a slightly different fashion than is done in the text. So you'll see two different ways to do it. They're fundamentally the same, but approached slightly differently. So we have two tanks. Tank A, it's air, 0.1 cubic meters, 300 K, 500 kPa. It's connected with a valve, the tank 2. B, we have air, 1.2 kilograms, 450 K, 250 kPa. So the pressures and temperatures are different, and these are the two substances. We're told they're adiabatic. They're adiabatic, so Q is equal to 0. And so we drew a sketch. So what we're going to do is open the valve and let things come to equilibrium, and we want to find various temperatures, pressures, etc. And so here are our systems. And so we drew a sketch. The substance is air, so it's an ideal gas. The process is Q is equal to 0, delta KE is equal to 0, delta PE is equal to 0, the work is equal to 0. My heavens, almost everything is going to 0 except the change of internal energy. So now let's write the first law and see what that is. So Q is equal to delta U plus W plus delta KE plus delta PE. And everything goes to 0 except delta U. So what this says is that delta U equals 0, or that U final equals U initial. And let's look and see what the final one is. So the final one is basically where I have the two tanks together. So I have A and B, and I could call these so I have these two things together form the final tank. And so what I want to do is then U initial is equal to UA plus UB, and U final is equal to UAB, where they're joined together at the same temperature and pressure. And so now what I have to do is go about and find what the values for internal energy for each of the tanks individually, and then finally when they're together. Here, I'm given the mass in B, so I need to find the mass in A. So MA is equal to PV over RT for A is equal to 500 times 0.1 divided by 0.287 times 300. So I have that MA is equal to 0.58 kilograms. And MB is equal to 1.2. And so MAB is 1.78 kilograms. I have 1.78 kilograms for the final one. And now what I'm going to do is set up this equation where U initial is equal to U final. And so I have MA, CA, C sub B, TA, plus MB, C sub B, TB, is equal to MAB, C sub B, T final. And what I'm going to do is substitute in. I see that C sub B's cancel. And so if I look at this, I have 0.58 times TA 300 plus 1.2 times TB 450 is equal to 1.78 times T final. And I'm able to get T final is equal to 401.1 degree K. And so now what we want to do is we want to find the final pressure. And if I look at it, if I want to find the final pressure, I have PV equals MRT. I need to find the final volume. And so what I want to do is find the final volume, which I know is the sum of the two volumes. And in this case, I was given the volume. Here I wasn't given the volume, so I need to find the volume for B. So let's do that. So VB is equal to P is equal to MRT over P. B is equal to 1.2 times 0.287 times 450 divided by 250, where we have that V sub B is equal to 0.62 cubic meters. So VAB, if you will, is equal to 0.72 cubic meters. I've added 0.1 to this, and so now I can find the final pressure. So P final is equal to MRT final, and I'll have here PAB, since that's how we denoted this. So this is equal to 1.78 kilograms times R 0.287 times the final temperature 401.1 divided by the final volume 0.72, and it gives us P final of 284.6 kPa. So I'm able to find the final condition. So in this problem, I did first law that enabled me to find the temperature, and then I used my ideal gas equations of state PV equals MRT to find other values. Now what I'd like to do is to look at balloons, helium balloons, and why balloons go up. And so there's a very simple thermodynamic way to do this. So it works for hot air balloons, helium balloons, whatever, balloons that go up in the air. So if I take a balloon, and let's just say I'm going to have it be helium, and I'll have it, if I want it to be a helium balloon that's carrying something, I'll have this. So I have helium in here, I have air outside, and we know, even if this is a little kid's balloon, if you let go, it goes up in the air. And why did that happen? So we're interested in this, and we want to be able to look at what these are. So what's happening is there's a difference between the masses involved. So we know that F equals MA, and for our cases, F is equal to mg. And what I'm interested in is this volume. So I know that the volume V is equal to 4/3 pi r cubed, which is equal to pi over 6 d cubed. So this one you probably remember, this one is a little bit easier to use. And now what we're looking at is we're looking at what is the lifting force. So I want to find the lifting force. So the lifting force F is going to tell me how much weight I can have in here, not how much mass, how much weight I can have. So I'm interested in the lifting force, what's making this go up. And basically, it's the difference in the mass between the mass of helium in this volume and the mass of air that would be in the volume. So I look at the mass of air in the volume. So I look at mass of air displaced. And I look at the mass of helium. So if I have Ma and MHHE, the difference between these two is delta M. And the lifting force is very simply F is equal to delta M times G. So this is the lifting force that makes the balloon go up. So now let's look at what the lifting force would be if I take a 1 meter diameter balloon. I'm going to put helium in it, and we'll see what happens. And part of it is we can see there's a big difference between the gases. If I look at R of helium is 2.077, and R of air is 0.287. So there's a big difference between these two, and if I apply the ideal gas law, M is equal to PV over RT, I can see that if the pressure and volume are the same and R is less or greater, it's going to affect the mass. So, for helium, there's not going to be as much mass because R is a much bigger number. Air is a smaller number, so the mass will go up for air. So now, let's be given this information about the size of the balloon, the temperature, the pressure, and we'll look at what the lifting force is. So for D equals 1.0 meters, T is equal to 300 K, P is equal to 100 kPa. So it's basically standard pressure and temperature, and the volume is pi over 6, 1 cubed, and so that's equal to 0.523 cubic meters. The mass of air is equal to 100 times 0.523 divided by 0.287 times 300, and it's 0.6 kilograms. And I'm going to do the same thing for helium. I'll find the mass of helium. The mass of helium is 100 kPa times the same volume, 0.523, divided by 2.077 times 300. And this is going to be 0.084 kilograms, much less mass. And so delta M, so the lifting force, F, is equal to delta M times G, is equal to 0.6 minus 0.084 times 9.8. And if we do this, we'll get the lifting force is 5.8 newtons. Have to check. And so anyway, it gives us the lifting force. I was checking to see if I made a math error, so that was what I was looking at. And so now so this gives us what the lifting force is. So we can see what the lifting force would be. So we could lift up about half a pound, half a kilogram of mass. And so for homework, do 513, 521, 523, 527, and 537.